Assalamualaikum to Dr. Hairul Jabbar. So today I would like to present to you about the project assignment using Vivado software. So I would like to share my screen. Okay, as you can see here, first of all, I will show you the coding for the IP core FIFO generator, first in, first out. So we're going to use 8-bit to 8-bit. As you can see here, the coding declare that the input used as 8-bit input data and produce output 8-bit output data. So as we run the simulation, okay, so this is from the previous result. So now I will reset over again and make a new one. Post constant 1. Okay, output data will become 0. Read data will become 0. Okay. So we turn off the reset button and enter the value. So constant called 0. In data valid as acting as enabler. So if we enter the high voltage, which means 1, then we allow the data to enter our FIFO generator. For the read data enabler, we do not need to enter high input yet because we not going to read the data first because we want to enter the data. Okay, so enter data 111 unsigned decimal. Okay, as you can see here, this is the data. Okay, so this is data in data valid 1, which means that the data has already entered our FIFO generator. And next data will be 112. It can be any number as long it is not 8 bits input, which is 2 to 5. Okay, that's constant. In my case, I'm gonna enter in 1 1 1 2 1 3 1 1 4. Okay, so here we go. 113. Next is 114. Oops, this need to be setting to the unsigned decimal. Okay, so as this data is entered, so we're gonna turn off the enabler for data valid for the input data. Post constant, post value will become 0. Read data will be changed to 1. Okay, we shall see the output. Okay, yeah. Okay, so this is the result for our presentation. I mean, for 8-bit to 8-bit. When we enter 8-bit, it will produce 8-bit output. Okay, so next, I will show you for the 8-bit to 32-bit, to 16-bit, I'm sorry. So this is the coding, exactly same like the previous coding, but only this time we change the output into 16-bit. Okay, so we change here, and the part from our FIFO generator, if we double click this, we can change the properties. Okay, so next for the simulation. Okay, so I'm gonna reset it We set it first. Post constant 1. Okay. For the data will become 0. Read data will become 0. Okay. So, okay. So there's no data yet in the FIFO generator. Okay. So we turn off the reset button into high in data valid, in data, enter 111, unsigned decimal, in data valid, high. Okay. See? Okay, next data was constant 112, unsigned decimal. Okay. So here we can change the data into any type of number, unsigned decimal, binary, hexa, or octal. It depends on which type of data we're going to use. So 113. Okay, so and 114. Post constant 114. Okay. Okay. So we turn on the read, we turn off the in data valid first into 0, read data into 1. Okay, and we see oh, okay, there's some mistake here. I forgot to turn off the reset button. It's okay. I will continue. I will try again. Was constant. Was constant 0. It is because all the ways along the data enter, the reset button is on. So no wonder there's no data in the FIFO generator. Was constant 0. Read data was constant 0. Reset to was constant 0. Okay. Okay. So it become available again. Okay, so for the in data valid was constant 1. Input data was constant 111. Unsigned decimal. Okay. And was constant 112. Unsigned decimal. Constant 13. Unsigned decimal. Constant 114. Unsigned decimal. And turn off the enabler for input data and open the enabler for the output data. Okay. Okay, so we're going to change these radix into hexadecimal. And here we go. Data show. Okay, so the question is, why the output data for the 8-bit to 16-bit produce two data stick together? As we can see, 8-bit to 8, this input is 8-bit and this input is also 8-bit. When we demand to produce the output for 16-bit, so the FIFO generator just add the two input together. What 7172, okay, is a combination of this input and this input. Okay, So proceed to the next 8-bit to 32-bit. Okay, so this is the coding for the 32-bit. Same as before, only change the part that we need to change, which is the output 32, and also the properties from the IP generator, which we can change here. Okay, next. So I will show how to get the 32 output. So first constant 1, first value is 1, reset. Okay, input data, first constant 0, first constant 0, first constant 0. Okay, okay. So turn off the reset button, first constant 0, input data valid, first constant 1. Okay, this one first constant is 111, unsigned decimal. Okay, so this is data, this is the first data enter, change to unsigned decimal. Okay, it can be anything, can be any types of number, depends, but in this case I'm just going to use the unsigned decimal. Okay, so 122. Okay, first constant 123, unsigned decimal. Okay, and its number is 144. Okay, okay, so for read data, turn off the input data valid, first constant turn to 0, read data, first constant turn to 1, and the output will show. Okay, here we go. Okay, credits turn into hexadecimal. So here it is, seed F, 7A, 7B, and 90. So why is the output produced is 4 columns combined into one? It is because when we enter the input, the one input is determined by only 8-bit. So if we demand to produce to show the 32-bit, FIFO generator will combine 4 input together, 8 times 4 equal to 32, and will produce the output, which is 4 columns combined to 1. Okay, that is all for my part, and my partner will present about the comparison between the 3 experiments in terms of power, speed, area, and size. That's all from me. Thank you.
Assalamualaikum, I bid to Dr. Hayul Jabbar. My name is Muhammad Firdaus, and now I would like to continue our presentation about our project, which is the FIFO Generator. As you know, we have 3 IP cores for the FIFO Generator. The first IP core is the 8-bit to 8-bit of FIFO Generator. Second one is 8-bit to 16-bit of FIFO Generator, and the last one is 8-bit to 32 bits of FIFO Generator. So for the first part of my presentation, I would like to compare the 8-bit to 8-bit FIFO with the 8-bit to 16-bit FIFO. So as you can see, this is the 8-bit to 8-bit FIFO, and this one is the 8-bit to 16-bit FIFO. So now I will go to the summary of the simulation. As you can see, both of these IP cores has been completely synthesized and implemented in this simulation. So for the result of the implementation, I would like to discuss about the timing, the utilization, and the power. Let's go for the timing tab. So for the 8-bit to 8-bit FIFO generator, the worst negative slack is negative 3.60 nanosecond, and the total negative slack is negative 28.313 nanosecond. Next is for the 8-bit to 16-bit of the FIFO. The worst negative slack for the 8-bit to 16-bit is negative 3.73 nanosecond, while the total negative slack for this simulation is negative 58.036 nanosecond. Okay, the number of failing endpoint is the number which is this is the 8-bit to 8-bit FIFO, while this is 8-bit to 16-bit FIFO. Next is the utilization. As you can see, the utilization for the 8-bit to 8-bit FIFO and the utilization for the 8-bit and 16-bit FIFO is almost the same, except for the I/O part. So for the I/O in the 8-bit to 8-bit FIFO is 10%, while the I/O in the 8 to 16-bit is 14%. But the LUT, the FF, the BRAM, and BUFG is same, which is 1%, 1%, 1%, and 3%. Lastly, I will discuss about the power for the simulation. So the total on chip power for the 8-bit to 8-bit FIFO is 0.107 watt, while the total on chip power for the 8-bit to 16-bit of the FIFO is 0.108 watt. The junction temperature for this both IP core are the same, which is 26.2 degrees Celsius. Same goes to the thermal margin and the effective power. The thermal margin for both IP core is 58.8 Celsius, while the effective power is 11.5 watt. Okay, that's all for the comparison for the 8-bit and 16-bit of the FIFO generator. Now I would like to show you the last IP core in our project, which is the 8-bit to 32 bits of FIFO. So as you can see, the 8-bit and 32-bit of the FIFO IP core has been completely synthesized and implemented. So for the timing result, the worst negative slack of the 8-bit to 32-bit of the FIFO is negative 3.999 nanosecond, which is almost negative 4 nanosecond. And the total negative stack is negative 120.469 nanosecond. The number of failing endpoint is 32, which indicate this is the 8-bit to 32 bits of FIFO. Okay, next I will show you the utilization tab. As you can see, it is still the same as the 8-bit to 8-bit and 8-bit to 16-bit of FIFO for the LUT, FF, BRAM, and BUFG. But for the I/O in the 8-bit to 32-bit of this IP core, the I/O is 22% in the utilization. I will talk about the power consumption of the 8-bit to 32-bit of FIFO. The total on-chip power for the 8-bit to 32-bit of FIFO is 0.1080 0.109 watt, and the junction temperature is 26.3 Celsius. The thermal margin and the effective power is still the same from the previous IP core, which is 58.7 Celsius and 11.5 watt. So what I can conclude for this simulation, there is a slightly different between the power, which is the power for the 8-bit to 8-bit FIFO is 0.107. The total on-chip power for the 8-bit to 16-bit is 0.108 watt, and the total on-chip power for the 8-bit to 32-bit total on-chip power is 0.109 watt. Same goes to the utilization. The difference between the I/O utilization for all IP cores are different, which is the 8 to 32 bits of FIFO is 22%, the 8-bit to 16-bit of FIFO is 14%, and the 8-bit to 8-bit is 10%. Okay, that's all from our presentation on the result of the project. I hope you understand about our project. Thank you for listening to our presentation.
Okay. Next, I would like to proceed to the next part of the question, which is discuss methods that can be used to optimize the architecture to achieve higher efficiency. First of all, I would like to define what is the higher efficiency. So higher efficiency stands on less response time, which is the shorter response time, the better. And when the architecture use all the resource allocations, and in my opinions, I would like to suggest or propose on the method which is we need to more focus and improve on the architectural design, which is when we designing the architecture, we can also provide or the which is we use higher computational power of processor by insert the more processor, it will increase it will increase the response time. And also we could use a higher memory capacity, which will result in the speed of the architecture efficiency. And also we can also use a hardware that consume a low power consumption. So by these three methods that we focus on architectural design, it might able to improve the efficiency, which is what I stated earlier. The less will be uh, less response time and use the all of the resource allocations. That's all from me. So my partner will continue with the next question.
Okay, the next question is discuss the possible contribution to society based on the embedded system design knowledge and the experience in terms of designing better products. Okay, as we all know, the embedded system is one of the most important system in our daily life. The example of the embedded system is a digital camera, a wireless router, and a microwave oven. Okay, in my opinion, for the contribution to society is the embedded system design has reduced the size and cost of the products. For example, the digital camera. Okay, nowadays, digital camera can be found in our smartphone. Therefore, user can bring their smartphone with their digital camera anywhere. Therefore, they can take any picture that they want to take anywhere they want, and it is a very conventional and high in reliability. That's all for me. Thank you.